In this tutorial, we're going to learn how to apply kFold cross-validation in R. And specifically, we're going to apply logistic regression within kFold cross-validation. Now, we could apply other types of statistical models within a kFold cross-validation framework. However, for simplicity, we're going to focus on logistic regression because it does use binary or dichotomous outcomes, which makes it possible to think about things in terms of classification tables and so forth. And so that's what we're going to focus on today. Now, let's do a quick overview of what kFold cross-validation actually is. So imagine you start with a sample of data and you want to make sure that this sample of data is sufficiently large because we're going to do a number of partitions or splits to the data. So the first step that we typically take is that we're going to take our original data and do an 80% 20% split. So we'll randomly assign our data from either the training data group or the test data group. And so 80% of those random cases from our original data will go towards the training data and 20% will go towards the test data. Now this 80-20 split is fairly conventional, but you could also do a 90-10 split or you could do a 70-30, whatever makes sense in your context. So the next step is that we're going to focus on this training data set. So the next thing that we'll do is we'll partition the data even further. And specifically, we're going to partition the data into subsamples, or just simply called samples here. And so what we'll do is we'll create K samples. Okay, and again, we're going to use random assignment here. Now the number of samples will be equal to K. So K samples, and this is where kFold cross-validation originates in terms of the name. So we'll have K samples. In this case, you can see we have 5 samples all the way up to K total. Okay. And then we can then create partitions within, and we can then validate within this sample. And this is where the cross-validation process comes in. And we create folds. And I'll show you that in a secondary example of this that'll bring it to life a little bit more. Okay, so here we carry out our kFold cross-validation process. And ultimately from that process, we're going to end up training or building a final model that's based off of the results of each one of these folds that we've just run. Now, the next thing that we're going to do, and this then brings it into what we consider to be a more conventional or true predictive analytics framework, is that we're going to take that test data that was really our holdout data from the beginning, where we had that 80-20 split, where 20% of our data was randomly assigned to the test data data group. We're going to now use that test data, and we're going to evaluate that model we trained with the training data. And the reason we're going to do this is we're going to see how well that model actually performs when we give it brand new data that this model has not seen before. And so we can look at things like prediction accuracy, classification accuracy, or whatever makes most sense when it comes to the type of model you're running within a kFold cross-validation framework. So as I mentioned, let's take another look at, let's take a specific look at an example of how kFold cross-validation might actually unfold. So again, we'll start with our original data. We do an 80% split where 80% of the data is randomly assigned to our training data and 20% is held out and assigned to our test data. So focusing on that training data, the next thing that we're going to do is we're going to do what we call a 5-fold cross-validation. So K equals 5 here, which means that we took our training data and we randomly assigned those cases to 5 samples or subsamples, however you'd like to call it. Now here's where the folds come in. Okay, so to actually carry out the kFold cross-validation process, what we're going to do is this. The first thing that we're going to do is we're going to create fold number 1, which is we're going to combine 4 of those samples. In this case, it's samples 1, 2, 3, and 4. And we're going to combine those data and we're going to estimate or train a model based on those data. And then we're going to validate that model on the holdout data set here, which in this case was sample 5. So this is our first fold. Okay, so we'll get the results of the model estimation from this first fold. We'll then repeat that process for the second fold, and this time you'll note that we're using a different subsample or sample. In this case, sample 4 is going to be our holdout or validation sample, and then we're going to actually train the model using samples 1, 2, 3, and 5 this time, and then again validate on sample 4. And then we do this again for fold 3, fold 4, all the way up to fold 5. Okay, and so you can see for each one of these folds, it's just K minus 1 in terms of the number of samples that we're using to actually train our model. And so then we synthesize the results across all 5 of these folds here. And then that results in an overall final trained model. And as I mentioned before, the next thing that we're going to do is we're going to evaluate the model. And how do we evaluate that model? We evaluate the model using the test data, which again, the test data have not seen this model that we've just trained here. Okay, these are fresh data, and we are going to then apply these data and to this model here. And so we're going to then, we're going to apply the model to these data. And this will result in, we can get information about model fit, prediction accuracy. And in the case of logistic regression, if we're running that type of model within our kFold cross-validation, we can get classification information as well. So how many cases were properly classified into each level of the dichotomous or binary outcome that we're interested in. So this is a little bit of a crash course on what kFold cross-validation is. And so now we're going to focus on how to bring that to life in the R context. And so as you can see here, I've got an R script window editor that is opened right now. And I note here using the hashtag annotations that we're doing kFold cross-validation in R, and we're going to be using logistic regression in this framework. Now, the next thing that we're going to do is, of course, set our working directory, and I'll move through this step fairly quickly. So we're setting our working directory. And I happen to know, using the setWD function, that my working directory is my H drive, and it is my R workshop folder. Okay, so H:/R workshop is where my data live, and I'm putting this all in quotes within the parentheses of the setWD function. So I can run that, and as you can see down here, my console reflects now that I have now set my working directory to my R workshop folder that's within my H drive. Now, the next thing that I want to do is read in the data that I'm going to be using today that comes from that R workshop working directory that we've just specified, or in other words, the folder that is called R workshop within that H drive folder. So let's read in the data. And to do so, I'm going to be using the reader package, which is part of the tidyverse, and specifically the read_CSV function within the reader package. Now, I have very recently installed the reader package, so I'm not going to run through that just to save time. But if you do need to install the reader package or you need to update it, run this line of script here. You will definitely need to run the library script though, and specifically the library function to access the reader package and the function that we're going to use within it. So here I put library function with reader in the parentheses. I click run. We access that with no problem. The next thing that I'm going to do is I'm going to read in the data, and I'm going to call the data frame object that I read in df, very generic. df, I'll say that stands for data frame. And I'll use the left-handed arrow operator to assign the data frame to this object that we'll call df. And I mentioned before, I'm using the read_CSV function from that reader package. And within the parentheses, the sole argument is going to be the name of the .csv file that I'm going to read in. And it is called Predictive Analytics.csv. Predictive Analytics.csv with a capital P and a capital A. There's no spaces in here. Remember, R is case and space sensitive. So I'll run this. And as you can see, the data have been read in here. And these data, you'll remember, if you are using the read_CSV function, which is a part of the tidyverse, as I mentioned before, this actually reads it in as a special type of data frame, which is called a tibble, that's specific to, or not necessarily specific to, but that is generated within the tidyverse and worked with. Okay, so that's something to keep in mind because that'll come up a little bit later. So let's take a look at our data. So in our data frame, we have a unique ID variable, which is just ID. Our outcome that we're going to be focusing on today is turnover, where let's say that 1 equals someone voluntarily quit the organization and 0 indicates that they stayed. And let's say the time frame here is this is turnover data from a 1-year or 12-month period. Now we have 4 different variables that we can use to predict turnover in this case. We have JS, which stands for job satisfaction, OC, which stands for organizational commitment, TI, which stands for turnover intentions, and then NAF, which stands for negative affectivity, which is a person's their propensity or their dispositional tendency to engage in negative emotions and so forth, like anger, anxiety. Okay, so I'd also like to use the STR function to actually look at the data frame in terms of what are the variable types of each variable within the data frame, because often that will become relevant. So it's STR with the name of our data frame in the parentheses. Let's run that. Okay, so let's see what we've got here. All of the variables are numeric, even the ID variable. Okay, so we can tuck that away in the back of our minds for now. Okay, now the next thing that we're going to do is we are going to convert the our outcome. We are actually going to now install the caret function. And the caret function is great for predictive analytics and machine learning, and it's going to facilitate our ability to run a kFold cross-validation today, as well as to partition the data, which is going to be the first thing that we do. So as we always do when we're installing a package, we can use the install.packages function, and it's caret all lowercase. We put that in quotation marks. It's C-A-R-E-T, so not C-A-R-O-O-T like the vegetable, but C-A-R-E-T. And I have very recently installed and updated this package, so I'm not going to run this line, but most likely you will need to run this line to do the install for the caret package. And you will definitely need, though, to run the library function with caret as the sole parenthetical argument, which you can see here. And I'll run that. As you can see, it's loading right now. We see the stop sign appear here in our console window. Okay, so voila, now we have access to our caret package. Now, the next thing that we're going to do is we're going to engage in the partitioning of the data. And this is simply to, what we're going to do is we're going to create an index matrix of the selected values, okay? And so you'll see what this looks like in just a second, but we're going to be partitioning the data, okay? And so to do so, let's first set, I'll just to note this a little bit more, I'll add a few extra hashtags there just to make that stand out a little bit more because we're going to do some nesting here. The next thing that I want to note is that before we do it, let's do a random seed, okay? And so to do so, we'll use the set seed function, set period seed, and it's all lowercase. And you can put whatever numeric value you want in the parentheses. I'm putting 1985 in here, or 1985. And what this does is it allows us, whatever random split we're about to do, you can't see it, I'm doing air quotes behind the scenes when I say random split. It's not entirely random because we're able to reproduce it if we set the seed ahead of time, okay? So this way, each time you run through this script, you can get the same results. Now, I will say that sometimes they tweak the algorithms that underlie the functions that you can use for kFold cross-validation and other types of machine learning and predictive analytics models within the caret functions. And for that reason, sometimes even when you set a seed, if there's maybe a year has passed between when you last ran these models, sometimes you will see some subtle differences or sometimes some notable differences as the algorithms improve over time, okay? All right, so the next thing that we're going to do is we're going to let's just say create the index matrix. And this is going to allow us to index our data frame so we can do that random 80-20% split that I mentioned before at the beginning of the video. Okay, and so the first thing that we're going to do is we're going to create an object. I'm just going to generically call this object index, all lowercase. This is going to we're then going to assign our partition data, our index matrix values to this object that we call index. So I'm going to again use the left-handed arrow to do that variable assignment. And we're going to use our first function from the caret package, and it's called create data partition. And you'll notice that it's create data partition with a capital D for data and capital P for partition. Now, the first argument is we're going to specify the name of our data frame, which is df, lowercase, and the name of our outcome variable, okay? And so typically one little thing you might want to consider is that as we learned before, all of the data are numeric in this case. And sometimes if you do run a variable though, if your outcome variable is already a factor, that can be a little problematic when it comes to this partition. There's a quirky little thing where it will, let's say we want to do an 80-20 split. So that means that if we apply that to 1,000 observations, which is how many observations or cases we have in our data frame, that we would get 800 in our training data set and 200 remaining in our test data set. Well, if we have a variable that's of type factor, which sometimes can be the case, that's our outcome variable, sometimes you'll get something kind of quirky where it's for the 80-20 split, you'll get 801 applied to the split if you want an 80% split, when really it should just be 800. Okay, so one thing that you might have to do ahead of time is convert your outcome variable to a type character if it's a factor, or to numeric, or whatever makes sense in that case. Okay, in our case, we know that it's already numeric, so this shouldn't be an issue, but we shall see. Okay, the second argument is going to be p equals, and so this is the percentage equals, and really this is proportion though, because we're going to write it in proportion, 0.8, and this is simply that we want to create an index or randomly identify 80% of the cases, so 0.8. And then our next argument is list equals false. And so what does that mean? Well, that means that we don't want a list, which means that then by default, we will be getting a matrix. Okay, so the object we're creating will not be a list, it'll be a matrix. And then finally, times equals 1. And so this means if we set times equal to 1, it means we're doing one partition or split of the data, which is all that we want here. We want to split the data such that we just identify 80% of the cases, that's one split, okay? And then by association, there'll be 20% of the cases that are not identified. All right, so let's go ahead and run this line right here. Okay, so you see it successfully ran there. Now you'll see we have a matrix object in our global environment, and it's called index. Let's open it up here by clicking on it. And you can scan through here, and you'll see we have exactly 800 entries, which if you multiply 0.8 or 80% times 1,000, you get 800. And so that explains it. And so what you're seeing right here is you'll see that the row numbers here in the dark bold, okay, those range from 1 to 800 sequentially. But you'll notice when we look at the column that's called resample, because that's what we're essentially doing here, just we're randomly sampling from the data, you'll note that it doesn't include every integer between 1 and 1,000, which is what we originally had in our data frame. So if you look at our original data frame, you'll see that the row numbers go from 1 to 1,000 sequentially by 1. Here you'll notice we have 1, 2, 3, 4, 5, 6. Everything looks good so far, but then 8. So it goes from 6 to 8. And then it goes 9 to 10, 10 to 11, or 10 to 12, so it skips 11. And then you'll see all the way up to 1,000 here. Okay, so it's just selected 800 of these cases randomly. Okay, so we've created our index matrix. The next thing that we're going to do is we're going to apply this index matrix to our data frame so we can partition our data into that 80-20 split. Okay, so to do so, what we're going to do is let's create a new, first we're going to create a new data frame that let's call this, we'll say the first data frame will be the train_df data frame, and the second one will be the test_df, okay? So this is, again, if you recall at the beginning, we talked about that 80-20 split, 80% of the data go to our training data frame, the remaining 20% go to our test data frame, okay? So the first thing we're going to do is let's specify the name of the new data frame object. So it's train_df, all lowercase. Okay, you can see that there's a little warning message that popped up here. This is specific to what I'm doing right now. My R workshop folder within my H drive, I'm accessing that using a VPN. And it looks like that timed out a second ago. So I think I've just reconnected to it. So this should work just fine moving forward. Okay. All right. So let's now take a look at where what we're going to do. As I mentioned, we have our train_df data frame object. We're using the left-handed arrow operator to do variable assignment. The next thing that we're going to do is we're going to apply that index matrix to our data frame. And how do we do that? Well, we're going to specify the name of our data frame. Our original one is just df. Then we're going to use brackets. So the bracket notation here, because we're going to do matrix, we're going to reference using basic matrix notation here. And so to do so, the first argument within the brackets is going to be index and then comma, and then nothing after the comma. And the reason we're doing this is that we're saying by putting the index matrix object before the comma, we're saying we want to reference or index by rows here. If we had put this to the right of the comma, we would say we wanted to index or reference by columns. And as you can see here in our data frame, we're interested in referencing by the columns because those represent unique cases here. Okay, so let's go ahead and run that. And what you'll see here is that we get an error message. And I was expecting this. And so this is one of the reasons that it's good to think about the nature of the data that you're using, and also the types of objects. So if you recall earlier on, when we read in the data, I made a point of noting that we read in the data as a data frame object called df, but specifically when we're using the read_CSV function, which is again part of the tidyverse, we're actually reading it in as a tibble, which is a special type of data frame object or a special type of table. Okay, it has some extra bells and whistles to it. And there's some advantages to using it. Well, it doesn't always play super friendly with other functions and other packages and so forth. Now, sometimes you might find that this actually works, but based on the latest version of the Caret package, it appears that we need to take an extra step here to actually access or to actually index our data frame object. And simply what we're going to do is we're going to go up and we're going to convert our data frame of df, which is our original data frame, to an actual data frame from a tibble, okay? And so what we do is we're just going to overwrite the existing data frame by using df, the name of the data frame, followed by the left-handed arrow operator. And then we're just going to use the function that's called as.data.frame, okay? And then as a sole parenthetical argument, we're just going to put df for the data frame. So we're just going to make sure that this ends up being converted to an actual data frame, an old school traditional data frame object. Okay, so let's click run there. Now let's come down here and run this function again. It worked, okay? It just needed to make sure that we're actually working with a real data frame object here, okay? And so let's take a look at the new data frame object we have here. You can see it has 800 observations from our original 1,000, so that's 80%. That's a good sign right there. And so what you can see here is that we have just, if you look at our index here originally, remember it went from 1, 2, 3, 4, 5, 6, and then skipped to 8, 9, 10, 8, 9, and then 9 and 10, and then skips to 12. Well, we should see in our new data frame, it does that as well, okay? And so you'll see 1, 2, 3, 4, 5, 6 skips to 8, 9, 10 skips to 12. Okay, so this means that it's just applied and it's indexed based on those random 800 cases or 80% of the cases that we specified above. The next thing that we're going to do is we're going to create our test data frame. And so I'll just copy and paste that below and just change the name from train_df to test_df. And it's going to be the same notation, except we're going to do just a minus sign before index to say not this. So we're going to say not the index. So all else essentially from our original data frame object. Okay, so let's go ahead and run that. Now we have a new data frame object here, test_df. This is going to be our holdout data. And you can see there's 200 observations. So that's the 20%. We open it up and now you'll see it's all those cases that were not mentioned in the index. So we've got 7, 11, 18, 24, and so forth all the way until we get to 200 or 20% of the original sample that we had. Okay, so this is how we have just partitioned the data. So we've partitioned the data into our train_df and our test_df data frame objects. Now the next step is going to be to actually now run and is going to be to work with each one of these data frames, and we're going to adjust the outcome variable. And we're going to relabel the outcome variable, and I'll show you how to do that next. So to relabel the outcome variable, which again is turnover, we just referenced that here in the first argument of the create data partition function from the Caret package here above when we were partitioning the data. Now we actually want to make sure that this turnover variable, remember it's numeric. We saw that before up in earlier in our output here, that when we look at turnover, it's of type numeric in terms of the variable type. We want to convert this now to a factor. And before we do that, let's actually change the variable labels to something a little bit more meaningful, or rather I should say the value labels, okay? So we are going to relabel the values of the outcome. And again, we're doing this because we're applying logistic regression in the context of the kFold cross-validation today and the GLM function that's going to be used as part within the train function from the Caret package a little bit later on here. It does tend to prefer things to be of type factor. And this way we have more control too. We can make the outcome values a little bit more meaningful. And by meaningful, I mean of type character and then eventually of type factor when we do finish the conversion. Okay, so what we're going to do is we're going to make it so that 1 is equal to quit and 0 is equal to stay. And so that's all we're going to do now with this relabeling. Now we need to do this twice, okay? And unfortunately, that's a byproduct of the fact that we had to do this whole thing where we had to relabel or we had to convert the data frame object from Tibble to a traditional data frame object. Ideally, we could have done the relabeling at the very beginning of this process up here after we read in the data, but I anticipated that this was going to be an issue, and so now we're just going to have to do double. We'll do the relabeling for both the training data frame and the test data frame. Okay, it takes a few extra lines, but not too much extra trouble. So let's do data frame. So that's our df object, followed by $, and the turnover variable, which is our outcome variable. So we're just saying that we want to reference this outcome variable or this variable from this data frame here, and that's what the value of the $, is right there. And then we're going to use the left-handed arrow operator for some variable assignment here. I'm sorry, getting ahead of myself. We're going to use the brackets again here, and specifically what we're going to do is within the brackets, we're just going to repeat data frame, $, turnover. So we're going to reference that, and we're going to say, so when the outcome variable is equal to 1, okay, and outside the brackets, we're going to do the left-handed arrow here. We are then going to put text in quotes, quit, okay? So what this is saying is when the original turnover variable from the df data frame object is equal to 1, that is going to become quit, and this is going to overwrite our existing turnover variable from the df data frame object, okay? So the next thing that we're going to do is, oh, actually, and I'm sorry, this is going to be, we're now focusing on, I need to be specific here, that we're looking at the train_df data frame here. Oops. And so I'm just replacing the dfs with the train_df data frame. Okay. So I'm doing this specifically for the new data frames we've created. So I'm going to copy this line and paste it below, and I'm going to adapt it now. So now I'm going to just change 1 to 0 and put stay in the quotes here. So I'm just saying for the train_df data frame, whenever we have a 0 for the turnover variable, we are going to convert that to the character stay, which again, we put in quotation marks, and that's going to overwrite our existing turnover variable that appears in our train_df. So you can see it's all numeric here. We're going to replace these. Now I'll do it one at a time just to show you how this works. So click run. Let's go back up here to our train data frame, and now you see all the ones are quit. And let's do the same thing with the second line here. And now you see we filled it out. So all the zeros are stay. Okay, so whether people stayed or quit. Now the next thing that we're going to do is we're going to copy both of those lines, and let's come down below here. And all we're going to do now is replace the train_df with test_df. So we're just going to repeat this process for the test data frame object. So just replace all those instances of train_df with test_df. And let's go ahead, and so we'll see up here, it's originally, again, the test_df, it's zeros and ones. Run those two lines, and we should now see stays and quits. All right, so we're getting closer here. Now what we need to do is for each of these turnover outcome variables that are within these two data frame objects we have now, so train_df and test_df, we just want to make sure that they're both of type factor. And so we're going to convert the outcome variable to type factor. And this is going to look somewhat similar to the as.dataframe object from above, except we have a little bit more information we're going to include, and we're going to be focusing on a specific variable here. Okay, so we are going to, let's just copy and paste from the first data frame here, train_df, $turnover. So that variable right there. This is going to be what we're going to overwrite. So we're going to just overwrite the existing turnover variable from the train_df data frame object. And we're going to use the function to the right of the left-handed arrow, which is as.factor. So this is going to convert to a factor. This is a function from base R, just like as.dataframe, as.data.frame that we used earlier. And then as the sole parenthetical argument, we're going to type in the name of our data frame object, which is train_df, followed by $, and turnover. Okay, so we're just converting this turnover variable to a factor. So From likely it ended up becoming a character here because we converted it to text. Now we're going to convert it to a factor. And we're just overwriting the existing turnover variable from that train_df. Okay. And so let's now copy this line, and we're just going to do the exact same thing, except we're going to do this for the test_df data frame object. So just replace the two instances in this line of train_df with test_df. And let's run both of those. Okay, and so we can verify now if we've actually, and actually we can use the class function instead just to mix things up. Let's just make sure that train_df $turnover is of the appropriate class. Okay, so it's of type factor now, so that's a good sign. So it worked for the first one. Now let's do the second data frame in the turnover variable. So change train to test here, click run. Okay, it's of type factors. So we're good to go now when it comes to converting that outcome variable to a type factor. Okay, so all of this is in preparation now for our actual, for running the data here, okay? And one thing that, did I run that above? I'm actually realizing now that I need to make sure that I never actually ran that random seed here. And fortunately, this is a very easy fix here, because this is the beauty of R, is I'm just gonna rerun all of what we just did with that seed set there. So this way I can reproduce what I did before. Otherwise I wouldn't be able to reproduce. And you can see we've got everything back to what we just did. Again, the beauty of R here. Perfect. You'll see that it actually, the index is going to be different here, but we won't know the difference when we actually run the data here in just a second. We actually run the kFold cross-validation, which brings me to the next step here. So the next thing that we're going to do is we're going to actually specify the type of training method that we're going to be used, that we're going to use right now, okay? And the number of folds that we're going to specify. So this is where we're going to actually indicate that we want to do kFold cross-validation. And to do so, we are going to use what's called the train control function from the caret package. So we're going to use another function from that caret package. First, we want to make sure, though, that we're actually going to assign all this information we're going to generate here. These are going to be really the control specifications for the model that we end up running. So this is going to tell the subsequent function, our train function that we'll use in a little bit, what specifically type of framework we're going to apply here. And that is going to be a kFold cross-validation with 10 folds. Okay, so let's call this control specs. So CTRL SPECS, all one word, all lowercase. So this is the object that we're going to create over here. And we're using the left-handed arrow operator again to do that. And then we're going to do the train control function from the caret package. And note that it's all lowercase except for that C in control. So train control. So the first argument is we're going to use the method argument and say equal to, and in quotation marks, CV. And so that stands for cross-validation. So we're saying we want a cross-validation method here. And then we're going to do comma to the next argument, which is going to be number equal to. And this is where we're going to specify the number of folds for our cross-validation. So this is kFold cross-validation. See, I'm missing an N here. Okay, so those are the first two arguments there. And let's actually drop down to the next line here so I don't run out of space here. And the next thing that I'm going to do is I'm going to specify save predictions as the next argument. So save predictions with a capital P for predictions. And I'm going to say, let's save all the predictions and make sure you put all in quotation marks. And then finally, I am going to specify the class probs equals argument. And I'm going to set this to true. And what this means that in addition to our predictions, I also want to save the class probabilities as well. All right, so we should be ready now to run this function right here and create this new object that we'll call control specs, or CTRL specs. Let's run that. Okay, so you can click on it here. Okay, this will mean very little to us. This is essentially all the information that we're going to then plug into the subsequent function. So this is what's stored in that object we just created, control specs. Okay. All right. So the next thing that we're going to do is let's set a random seed once more. And because we needed a random seed to do the partition of the data, which we did above, and now we're going to need a random seed because we're also within the kFold cross-validation we're going to run. There's going to be, if you recall from the beginning where I showed you the visual of what kFold cross-validation actually looks like, for each fold or each sample that we're going to use to create the folds, we actually have random assignment from the test_df data frame object. Okay, so I'm just going to use set.seed, and this time I won't forget to run it. I'm going to use the same numeric, you can put whatever numeric value you want in here. I'm going to use the same 1985 or 1985 here. I'm going to make sure I run it. Okay, I've set my seed there. And now the next thing I'm going to do is I'm going to specify the actual model that I'm running here. Okay, so in the model, I mean the statistical model, which is going to be a logistic regression model. So up here, I specified that the framework for the training method we're going to use, which is the kFold cross-validation. And then down here, I'm going to specify the logistic regression model, and we're going to be using the train function from the caret package. And then within that, we're actually going to reference the GLM function, which is a base R function that we can use it for a generalized linear model, GLM, that we use for logistic regression often. Okay, so as we always want to do when we're specifying any type of statistical model, or at least with most functions that we use, we typically want to create some kind of object that we can subsequently reference and summarize. So let's call this first model, let's just call this model 1, all lowercase followed by 1. And again, we're going to use the train, all lowercase train function from the caret package. And the first step is we're going to specify our model. Okay, and this is just going to be specifying a logistic regression model. I'm coming down here to the console just to make sure I can get the names right of the variables. So I'm doing names function, and let's do train_df to get the names. Okay, so here are the names of the functions, or rather the variables from our data frame object. So I'm going to do turnover is going to be regressed onto JS plus JOC plus TI plus NAFF. And so we're saying turnover is regressed onto job satisfaction, organizational commitment, turnover intentions, and negative affectivity. So we're going to see how well these predictors can predict the dichotomous or binary outcome of voluntary turnover here. Okay, so that is our first argument, is specifying the name of the model. We're going to go down a line, but the second argument you can put on the same line if you wanted to, is we're going to specify the name of the data frame from which these variables come, which is train_df. Okay, so we're using the training data here to run our kFold cross-validation. And we'll come down to the third argument here. All these arguments are separated by columns. And we'll do method equals GLM. Put GLM in quotes, and this stands for generalized linear model, which is the family of analyses that logistic regression lives within. And specifically, speaking of family, we want to use the next argument is going to be family equals, and this is where we're going to specify binomial. Okay, and you don't need to put binomial in quotes here, but binomial essentially means that we do have bi means two, and so here this is relevant because we have two levels to our outcome variable, stay versus quit, so it is a binary or dichotomous outcome variable. And then finally, our last argument, we are going to do tr control. Okay, so that's tr with a cap and then followed by capital C and control. Okay, so tr control is equal to ctrl specs. So this is the specifications that we created above here, where we're saying, okay, we're going to train this model using kFold cross-validation. So we could put this all within the train function. This saves some space here, okay, or it makes it a little bit less clustered instead of having to nest these things. But we're saying tr control here, and let's go ahead and run this. Okay, we saw the little stop sign. It looked like everything ran. It's blue, so that's usually a good sign. There's no red text below that says warning or error. So generally, that means we're in pretty good shape here. So let's go ahead now and take a look at what we got. So let's use the print function from base R and just type in model1, the name of the object that we assigned our model estimates to and all the model information that we just ran here. Take a peek here. Okay, so we can see some general information about our data here. Just because we use the GLM function to do our logistic regression, it says generalized linear model here. It says 800 samples. It really means 800 cases here. We have 4 predictors, so 1, 2, 3, 4. That checks out. And then 2 classes for our outcome variable or dependent variable, quit versus stay. That should look familiar. Okay, so that's our outcome variable is turnover here. And then it tells you in terms of, okay, we did 10 folds. So remember we specified number equals 10. That gets reflected here. We said method CV. So that's cross-validated. So this is saying right here, essentially kFold cross-validation or specifically 10-fold cross-validation. And then remember what we're doing within each one of the folds is we're collapsing k minus 1 of the samples that are created behind the scenes here. Okay, so as part of this whole process here, we're creating 10 samples from the 800 cases, okay? And then we are creating 10 folds, and within each one of those folds, we're taking k minus 1, so 10 minus 1, which equals 9. We're taking 9 of those samples, running or training the model, and then validating that model using that last sample we didn't use, that kth sample, the 10th sample, okay? And then we repeat that process 9 more times, okay, for a total of 10. And so here are the number of cases that appeared in each one of those folds. So 721, 720, so all around 720 or so, okay? And then we get the model accuracy statistic here. So this is the overall classification accuracy of predicting whether or not people stay or quit compared to their actual stay and quit based on using these predictors of JS, OC, TI, and negative affectivity there. And we see that, oh, not too bad. It's 0.698, so let's say 0.7, so 70% accuracy. And then the kappa value here is equal to 0.389. And this is another classification index here. And I'm going to cheat a little bit here because I didn't want to have to type this all out. I've actually stored some information here that I'll copy and paste in. So these are kappa rules of thumb here for interpretation. Okay, so you can see a kappa is let's say it's 0.39, just round that to 0.39. Where does that fall? Well, we'd say that it's about fair in terms of model classification. So we could say that kappa is fair. It's nearly moderate, but it is fair by these standards. Ideally, we're shooting for 1.0, which would be perfect to almost, or it's almost perfect to perfect if we had 1.0. Generally, we're not too happy about anything below 0.2. And especially not if we start getting down to close to 0 here, okay? So if we get anything close to 0, that's not going to be very good, okay? And I should say, let's actually put here, just to make this a little bit clearer. Yeah, anything less than 0 would be poor, okay? So that gives you an idea of what we're working with here. So at least initially we can say, well, this model did pretty well in terms of classification accuracy and our kappa statistic there. So you might be asking yourself, okay, well, what's the difference? Why do we have 2 statistics here, accuracy versus Cohen's kappa, okay? Or just kappa for short. Well, they do mean slightly different things. And so they're both useful for interpreting our models and evaluating our model in terms of how well they predicted and performed. And so when you seek accuracy, we're really talking about the proportion of total correctly classified cases out of all classifications, okay? So when you think about classified cases here, remember we have 2 levels to our outcome variable. It's quit versus stay. So what percentage of people were correctly classified, or what proportion of people were correctly classified into either stay or quit, and by correctly, if they were classified or predicted based on the model to be quit, what was their actual decision based on the observed data? And if it's also quit, then we would say that's a correct classification. If it was stay for that person in actuality, we would say that's an incorrect classification. So overall, again, 70%, not too bad for accuracy. Now, what's the difference then with Cohen's kappa, or just simply kappa? Well, kappa it's a little bit different because it's actually going to take into consideration and account for the baseline probabilities from your null model. And so what's your null model? Well, if you were to just say, remove all these 4 of these predictors from your model and just look at the model by itself, this is just looking at the baseline itself. So what would you expect just based on this outcome? And so it's basically accounting for, in other words, what are your baseline probabilities here? Okay, so what was the baseline? In the sample, was it 51% of the people said that they quit? Or was it 70%? Well, kappa can adjust for that. Okay, and so that's why where kappa can add some value as well. And so typically you'd want to report both accuracy and the kappa statistic here. Okay, so now the next step is let's actually look at the actual model summary. Okay, so actually look at specific information, not just the overall model performance in terms of accuracy and the kappa statistic, but let's also look at the output in terms of the regression coefficients themselves. Okay, because remember, we're going to find out whether JS, or job satisfaction, predicts voluntary turnover, controlling for the other variables in the model, and so forth and so on across the other predictors. Okay, and so to do that, we're just going to use the summary function from base R that hopefully you're familiar with already. And then just apply the name of the model. Again, it's model 1. That's what we specified up there. Click run. Okay, and so here's our outcome down here. We're going to focus on this right here, this table, which is the coefficients, regression coefficients to be more specific. Get our intercept for the model, okay, and this is a logistic regression model, so keep that in mind in terms of interpretation. And if you wanted to run if you wanted to run odds ratios and things like that and convert these estimates to odds ratios, you're definitely welcome to do that. If you want to know how to do that, I'm not going to cover it in this video to save time, but you can go to Logistic Regression in R to that video and that tutorial and learn more about how to do that and how to interpret odds ratios as well. But let's just focus on statistical significance here. Okay, and so as you can see, we get a little bit of a key down here with significance codes. And so if you see 3 asterisks, I guess you can say, well, let's just ignore that. Let's just focus on the fact that anything that is has an asterisk next to it, so here's asterisk equal to 0.05, that is going to indicate that's our threshold for our alpha level that we typically or conventionally use for determining statistical significance when we're using null hypothesis significance testing like we are here. And so what this is just saying is that anything with at least 1 asterisk is going to be statistically significant. Okay, if you had a period here, it would mean that it's the p-value is less than or equal to 0.1, but greater than 0.05. Okay. All right, and sometimes people will call this marginally significant. Let's not call it that. Let's just say that that's non-significant, especially when we have fairly large sample sizes here. Okay, and so we can see that all the predictors and the intercept, if you're looking at that as well, are statistically significant. So that's helpful to know. Okay, so all these significantly predicted voluntary turnover. Okay, but let's now take it a step further and let's assess variable importance. Okay, of the predictor variables. Okay, so we can actually see, okay, what is the relative variable importance of each one of these predictors? Okay, so we see here that that they have some different levels of significance. We see that their unstandardized regression coefficients are also of different magnitudes. But let's focus now on really which variable is most important for the prediction of our outcome of voluntary turnover. And we can use the var imp with a capital I, that stands for variable importance, so var imp with a capital I, and then just simply put model 1 as our sole parenthetical argument there and click run. And so this is going to tell you what, for the generalized linear model that we just ran, but specifically the logistic regression model, what the variable importance is. And so we can see that JS has 0 importance here when it comes to predicting voluntary turnover. And that might not be too surprising because this is the one that had only one asterisk next to it. So the p-value was only less than 0.05 and not less than 0.01 or 0.001. And we can see that turnover intentions, not too surprising here, carried the most importance, followed by organizational commitment and negative affectivity. Okay, so just some more information you can work with in terms of the actual relationships or associations within the model. In our case, really right now, though, we're interested in just coming up with the most predictive model. Okay, we're just trying to predict voluntary turnover with the variables we have. And so we're going to now assess that. And specifically what we're going to do is let's take this a step further, and we're going to apply our model to the test_df data frame. Okay, and so this is where we're getting into that true predictive analytics territory, because now we're going to apply this model that we've just estimated here, this model here. Okay, so this model was synthesized from all those different folds and model building and training that happened during the kFold cross-validation. This is our final model that we arrived at here. Okay, you could write out the regression equation if you wanted to. But we're going to apply that model to the data that this model has not yet seen. So this model saw the train_df data, because that's what it was trained on and what the kFold cross-validation was based on. But now we're going to apply it to fresh new data from that same original sample. So it's from the same population, presumably. And this way we can get a better look at how accurate our predictions actually are for this model. Okay. And so I'm going to nest this here, or rather make a higher level heading here by using 3 hashtags. And note that our first a step of this process is going to be predict the outcome using the model from train_df that we developed using the model applied to the test_df data frame. Okay, and so what we're going to do is we're going to create a vector of predictions here. So let's create just an object that we'll call predictions, all lowercase. And so we'll assign the predictions from our model to this object that we call predictions using the left-handed arrow operator. And so we're going to use now the predict function. It's just all lowercase predict. And then our first argument is going to be model1. Okay, so we are saying this is where we specify what model do we want to use to predict. And that's model1, which we just specified and estimated up here. That's the final model that we arrived at from our kFold cross-validation process. And then we are going to use the argument new data equal. And new data equals is going to be where we specify the name of that test_df data frame, that test data that we have not yet applied this model to. And so that's what we're going to do. We're going to say, okay, apply this model to the test data frame and see how well this model predicts turnover in this test_df data frame. Okay, so click run. Okay, so it looks like that was successful there. We can check down here and we can see that we now have values here in a vector, our predictions, or we can just run this here, the name of this object, predictions. And so here we get all of our predictions. Okay, so for each case, we get whether they were predicted to stay or quit. And so what this uses is a threshold too. So once it's predicting actually a numeric value, but then there's a tipping point where if it's above a certain value, then it gets classified as stay. If it's below a certain value, it gets classified as quit. So in other words, it's classified as a 0 or a 1. Okay, as opposed to a proportion or probability. All right, so we're now going to plug those predictions into a confusion matrix, which doesn't that sound like something that'll be really clear and easy to understand? Okay, this is actually a super helpful thing, and it's fairly commonly used when it comes to using predictive analytics, machine learning models, and so forth. And so we fortunately have a function within the caret package that's called the confusion matrix function. And it's confusion followed by matrix with a capital M. And as our first argument, we're just going to say the data equals predictions. So where does that come from? It's the vector of values we just created here, or the array that we created there. So that's our first argument. Our second argument is going to be specify the name of our data frame, which now we're working with the test data frame. So test underscore df, $, and then followed by turnover. So now we're saying we want to compare these predictions to the actual values, the actual turnover values here. So if you, for instance, just ran that chunk there, you'd also see a vector of values of stay, stay, quit, quit. And then we want to see how well these map onto or match the predictions. So this is where we get our classification accuracy, among other things in the confusion matrix. So let's go ahead and run that. All right, so let's take a peek at what we have going on here. Okay, so let's take a look and see what we have in the output here for the confusion matrix and the related statistics. And so here we start with a table here, a classification table. And so we can see the columns are going to be the reference, which is whether people quit or stayed in actuality, whether they actually quit or stay. So these are the actual observations. And then the rows are going to be the predictions, okay? So this is whether people were predicted to quit and stay. So we can see that 85%, and remember this test underscore df data frame sample has 200 observations. So 85 of the people who we predicted would quit actually did quit. 61 of the people who said that they would stay actually stayed. And so these are our true positives and true negatives here, if you think of it like that. But these are our errors in classification here. So 37% of the people who actually stayed, we had predicted that they would quit, and 17 of the people who said that they would quit actually ended up staying, okay? So for the final model, here's our accuracy statistic. This is similar to what we talked about already, the classification accuracy. It's 0.73. So that's actually, not too bad, 0.73. Here's the 95% confidence interval there for that accuracy point estimate there. And then we have the no information rate. This is essentially saying, okay, what percentage of people actually, the positive case here is quit, okay? So what percent of people quit? So it's 0.51, okay? And then the next thing that we have, oh, and here's the p-value associated for the accuracy statistic. This is less than 0.05, so that'd be considered statistically significant. And then for the kappa, we have that equal to 0.45, so let's say 0.457, so 0.456. Let's look at our table here. Oh, we're now in the moderate range there, so not too bad. And remember, kappa accounts for baseline probabilities, which would be 0.51 here for quit, and then by association 0.49 for stay. Okay, we'll skip McNamar's test p-value, and we'll now focus on sensitivity, specificity, as well as prevalence and so forth, okay? So we won't look at all these, we'll just focus on a few of them. So when we're talking about sensitivity, we're really talking about the number of cases whose observed data indicate that they were in the positive class, where the positive class here is notated at the bottom, or noted at the bottom here was quit, divided by the total number of cases in the sample, okay? So this is the number of cases whose observed data actually indicated that they were in the positive class, divided by the total number of cases in the sample. And so we see that that's 0.83, okay? Now with specificity, this is going to be the opposite of sensitivity. And so what that means is that we are just talking about the number of cases in which the positive class, oh, I'm sorry, actually I'm mixing, I was thinking of prevalence down here. So let's back up here and let's talk about sensitivity. So sensitivity, this is going to be, this will make a little bit more sense to you, hopefully. This is the number of cases in which the positive class, so in that case, again, is quit, was actually predicted, divided by the total number of cases whose observed data fall into the positive class, okay? So this is just looking at specifically those people who quit. So, and so this is the predictions, essentially the prediction accuracy for those people who are in the quit category. So how well did we predict those people who quit, okay? So this is narrowing things down from the overall classification accuracy we saw for the entire model, which accounts for both stay and quit, to just looking at the positive class of quit first. And then specificity is just going to be the opposite of that. So in other words, we're just looking at stay now. So the proportion of people that we predicted would stay relative to the overall number of people that that stayed. Okay, so that's 0.62. So we did a little bit better in terms of sensitivity than we did with specificity. Now, the prevalence, which is what I was talking about a little bit earlier before, this is just simply going to be, so you see it's 0.51. This is just going to be the same as this value here, because this is just the number of cases where the observed data were in that positive class, so quit, okay, divided by the total number of cases. And so this is just going to be our base rate, essentially, so our baseline probability for quit. Okay, if we knew nothing else, we could say that, and we wanted to predict who was going to stay or quit, we could say, well, based on our baseline probability of who quit and who stayed, we'd say that it's likely that, 51% of people in the future are going to quit, okay, within that time frame, which was, I think we said 12 months or a year for this sample, okay? And then finally, let's just take a peek at balance accuracy, which is this last value down here, which is 0.7279. So let's call that 0.73 or so. And this is going to be sensitivity plus specificity value divided by 2, okay? So it's going to be this value plus this value divided by 2, and that gives us the balance accuracy there. So we can test that out by just doing 8.3, oops, let's do it. Use parentheses here, 0.8333 plus 0.6224, then divide that by 2, so we're just getting the average, okay? And this should look familiar here, okay? So that's what the balance accuracy is. All right, well, that's all I'm gonna focus on here in the confusion matrix. And this is pretty much wraps up what I want to cover here when it comes to kFold cross-validation. This is, again, an introduction to it, but it is a good, if you have large enough sample, this is a great cross-validation approach to use. Standard cross-validation, you might just use one other sample. So you might just have your model, one sample that might just be your training data that you estimate the model based off of. And then you have your holdout samples, your test sample, which may be the remaining 20% of the data that you actually test the model's accuracy against. Well, that's perfectly fine in some situations, but when we have the advantage of having fairly large samples here, we had 1,000 people in our original data frame. That's pretty good. And so we can start thinking about doing something more intricate like kFold cross-validation and taking advantage of that larger amount of data that we have. And so in terms of deciding how many folds to use, here we decided on 10 folds, which is fairly conventional, but I'd say you can comfortably go down to 5 folds too if you'd like. But again, we have still standard cross-validation, which really doesn't use, it would just have one fold. So just be one set of data that we'd use, and then we'd apply that model we built towards our holdout test data. And that could be fine as well. But ideally, if we train the model on more folds, that's usually a little bit more ideal if we do have access to large enough data. So do consider when you look at each fold, what is the sample size within each fold? As we could see down here, I mean, our sample sizes were pretty good, 720-ish for each of the folds. We only had 4 predictors in our model down here, okay? And so that's something to consider too, is how big is your model and how big does the sample size really need to be to get reliable estimates for that model. All right, well, this wraps up the tutorial on kFold cross-validation in R.